Welcome to Tech Talks.
In this session, we will learn about critical disruptive voltage. So let us consider two conductors. This is conductor A and this is conductor B. The radius of the conductors are R and the distance between these two conductors is D, and this is the neutral point N, and we consider a point P. The distance between A and P is X. So this conductor is carrying a plus Q charge, this conductor is carrying a minus Q charge. So this is a single phase transmission line. Now the deferred distance between these two conductors D, this is to be kept in mind, is D is quite larger than the radius R of both the conductor, that is the radius of each conductor. Okay, and Q is the charge per unit length. Q is charge per unit length. Let us consider voltage P, that is the operating voltage. Voltage V, operating voltage, means this voltage is between this conductor and this conductor, voltage V. So the voltage between this conductor and neutral point is V by 2, and this conductor and neutral point is V by 2. Conductor A and neutral point is V by 2, and conductor B and neutral point is minus V by 2. Okay. Now also we have considered a point P at a distance X, at the distance X from A. Now we will find the electric field intensity at P. P is a positive charge, to be kept in mind, unit positive charge. Now we will calculate electric field intensity of P at point P. Now electric field intensity due to A on P will be repulsive, and due to B on P will be attractive. So the both charges will be additive in nature. So this is electric field intensity. Intensity Ex at P, it is given by Q by 2 pi epsilon 0 epsilon naught X plus Q by 2 pi epsilon naught D minus X. So this comes to Q by 2 pi epsilon naught 1 by X plus 1 by D minus X. Now this is Ex. Now if we want to find the potential difference between the conductors, then what we will do, we will be doing that V This is the potential difference between two conductors. V equal to minus Ex dx. Actually it is dV. dV is equal to minus Ex dx. Now if we want to find V, then it will be what? Minus integration of Ex dx. The integration limits will be what? The integration limits will be from t minus r to r. From t minus r to r. Okay. Now, as simply we will put values over here at minus r and t minus r. For Ex we will be putting values at this value, it is q by 2 pi epsilon naught 1 minus x plus 1 by t minus x dx, and we will get q by pi epsilon naught ln d minus r by r. This is V. Now since I have already told that this is true, that this r is quite smaller than d, so we can write this one as q by pi epsilon naught ln d by r. ln d by r. Now gradient at any point x can be easily found out by this formula, that gradient which will be the gradient from the center of A. Now from this formula we can find out what is equal to what is q. What is q? That is V pi epsilon naught by ln d by r is equal to q. We can find this from this equation. Okay. Now if we substitute this value of q, if we substitute this value of q in this equation, then we will get Ex equals to V by 2 ln d by r into d by x d minus x. So this is actually the electric field intensity between two conductors at any point. Okay, so this is for a single phase system. Now if we move on to a three-phase system, in case three-phase system, then this Ex, this is for single phase. If we move on to a three-phase system and do the derivation in the same way, then we will be getting V dash by ln d by r into d by x d minus x at any point x. Okay, this is for a three-phase system. And now here V is the operating voltage. Operating voltage means V is the voltage between these two conductors. So in a three-phase system there are three conductors. So what is V dash? V dash is actually voltage between line and neutral. Mainly the phase voltage in a star connection. Phase voltage. Okay. From this expression for gradient, it is clear that for a given transmission line, the gradient increases as x decreases. Okay, so in this both equation, you can see that since when x decreases, then Ex will increase. Okay, so the minimum value of x is when x is equal to r. That means this minimum value will be where? Here, r. Where it is at r. So at this point, Ex, that is the gradient, it is having its maximum value. Okay, so it is having its maximum value. So we will be calling it, if we put the r in place of x, then what we will get that the gradient G max is equal to ER. This is equals to E max, and V dash, we are talking of three-phase system now, V dash ln d by r to d by r d minus r. Okay, and we can also change this one to, this is nearly equal to V dash by ln d by r into, since r is very small with respect to t, so we can write it as 1 by r. So this is the value of Emax. Why this happens? Described earlier, because d is quite greater than r, so we can neglect this r, this d, and this d cancels out. Now this critical disruptive voltage, this is actually defined as the voltage, this critical disruptive voltage, this is actually defined as the voltage at which complete disruption of dielectric occurs. Complete disruption of dielectric occurs. So when I am talking of dielectric, then you can think of many dielectric, but first we will consider that we will consider air as dielectric. This is critical disruptive voltage C D V, where complete disruption occurs. Okay, so the dielectric strength is normally denoted as G naught, dielectric strength of air, and it is equal to 30 kilovolts per centimeter at NTP, normal temperature pressure, that is 25 degrees Celsius, temperature and 76 centimeter of mercury column. So what does this mean? It is total. What does that mean? That this total means what? This total means that so you are having two conductors at 1 centimeter gap. Okay, and both the conductors are placed at 25 degrees Celsius and the pressure is maintained at 76 centimeter of mercury column. So when the potential difference between the two conductors will be 30 kilovolt, then disruption of the air column will occur. That means what? You will be able to see spark between these two conductors. So that is what is called critical disruptive voltage. It is the complete disruption of the dielectric occur. Here the dielectric is air. See, similarly, when the temperature and pressure will be different, then the values of this point will change. So at any other temperature pressure, this is equal to G naught dash is equal to G naught into delta. So this is air density correction factor and is given by 3.92B divided by 273 plus T, where B is barometric pressure, barometric pressure measured in a centimeter of Hg, mercury column, and T is temperature. T is temperature measured in degrees Celsius. Okay, so the critical disruptive voltage is given by V dash equals to R G naught delta ln d by R kilovolt. Okay. The one more assumption is that here we have considered that the conductor is solid and the surface is smooth, but actually this is not so. The surface is not smooth. Surface of the conductor is not smooth. Okay, there are aberrations in a conductor, and also due to deposition of dust and dirt on the surface, the surface smoothness also hampers. So this affects the breakdown voltage of such conductors. Okay, how does it affect? That when the dust particles and other things deposits on the conductor, then the breakdown voltage of the stranded conductors is less than the smooth one. That means you require much lesser voltage than this one to disrupt the disrupt the dielectric, that is to disrupt the air. That means this voltage almost goes down. Okay, so these irregularities lies between these irregularities is taken care by another term, that is M naught. Okay, and for polished wire this M naught is 1. For polished wire, however, this M naught varies from 0.98 to 0.93 for rough wire. Okay, so this factor will also be added up in this formula. So the final modified formula will be what? The final modified formula, taking into this the dust particle issue also, will be V dash equal to R G naught delta M naught ln d by R kilovolt. Okay, so in this session we have talked of critical disruptive voltage, and we have seen that what factors affect this critical disruptive voltage. So this is actually the formula for critical disruptive voltage for single phase and three phase. Right? So we have also added over here that what will be the maximum value of this gradient. The gradient will occur when this x is equal to r. Then only the gradient will occur. So this is the maximum gradient that will be occurring over here, right? So this gradient for air is 30 kilovolt per centimeter. Obviously this condition should be valid, that is 25 degrees Celsius and 76 centimeter of mercury column. This total is called NTP, normal temperature pressure, as we have studied earlier in lower classes. Now this air density is not, if this air density and pressure changes, so this value of G will vary. So this G will be what? This G will be vary according to this factor. This is the air density correction factor, where the barometric pressure and the temperature is taken care of by these two variables B and T. Okay. Now there is also the final formula. So the formula converges to this part when we have taken care of different temperature and pressure. Also when the dust particles and other issues, for that also the critical disruptive voltage can change, and for that one the formula will be, another term is introduced, that is M naught, which is equal to 1 for polished wire, and M will be less. Why it will be less? If dust particles deposits on the conductor, then this value, this 30 kilovolt per centimeter, this will go down. If this goes down, then the value of M, the correction factor M, that will be going down. So for rough wire it is nearly around this part. So the final formula converges to this part. Okay. Thank you.